This is Unit 4, Video 4. This will be a short unit in which we talk about the 7 diatomic elements. Now, the 7 elements from the periodic table, when they are alone, which means when they are still elements, they will double up. Now, doubling up means 2 atoms of the same element combined together, and that's how the element exists. And these 7 are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. A fancy way of remembering it is by writing them together in this form, Hankel brief. Hankel brief. So make sure you bring your Hankel briefs when you come to chemistry. Another way of remembering these is by looking at the periodic table, because they create a 7 on the periodic table, visually a 7. Here they are. Here's nitrogen, oxygen, fluorine. It's actually the 4 halogens, fluorine, chlorine, bromine, iodine. We exclude astatine because it's radioactive, and really there's not much chemistry that we do with it because it's dangerous. But the others form a 7. However, there's only 6 elements here, and they point toward the 7th one, which is hydrogen. So here are the 7 elements. So anytime you see oxygen, oxygen will not be shown by itself just with an O, it'll actually be shown with an O2. Same thing for fluorine, same thing for bromine, and on and on. Now the reason why this happens is if you have chlorine by itself, each chlorine has 7 valence electrons, which we draw like this, and it's not complete. It does not have an octet, so it's not stable. It doesn't exist in this way as a monatomic element. It exists as a diatomic element. And to show you why, if you have another chlorine that also has 7 valence electrons, if they team up and decide to share an electron each, they'll actually become like an octet. They'll have 8 electrons, and that's exactly what happens. So the 2 chlorines will combine together, and now that line means they are sharing this pair of electrons, and now each of them has 8. This actually is 2 electrons. So if you count, each chlorine now has 8 electrons. This chlorine on the left has 1, 2, 3, 4, 5, 6, 7, 8, and so does the chlorine on the right. And this allows them to have an octet. So the octet, whoops, should be an O, octet, is why that these are diatomic, because they want to be like the noble gases. And then you can analyze oxygen and fluorine and hydrogen, and each one of them will do the same thing. Now hydrogen's octet will actually be like helium. Hydrogen wants to be like helium, so you'll see that 2 hydrogens will combine together and look like this. And this is simply 2 electrons, each brought by a hydrogen. And so hydrogen now can be like helium. So the reason they double up, the reason for diatomic elements, is because of the noble gases. Everyone wants to be like the noble gases. Alright, now when we see equations written, we're going to introduce you to more aspects of chemical equations. We've balanced them previously. You'll see what are called state symbols. Now, state symbols are symbols for the state or the phase. Remember, states or phases is the same thing that a certain chemical is in. And this could be solid, liquid, or a gas, usually. But here we're going to add one more. We're going to add something called aqueous. So, aqueous is this AQ at the back of the chemicals, and that means it is dissolved in water. So aqua, from the Latin for water, means this chemical right here, HC2H3O2, it's kind of a big chemical, is dissolved in water. So it's in the aqueous state. If you were to see this in a laboratory, what you would see is you would see this chemical, say in a beaker, but this chemical is actually dissolved in water. So this chemical is sitting in water, and that's a way to deliver the chemical to the reaction. Obviously the S stands for a solid, the L for a liquid, the G for a gas. This is actually an interesting chemical equation where you see all 4 state symbols present in one reaction. This is famously the reaction of baking soda and vinegar. This right here on the left is vinegar. This on the right side here is baking soda. When you mix vinegar and baking soda together, hopefully you've done this before, you get yourself carbon dioxide gas, you get a bunch of bubbling, so you get this product, you get a gas. Liquid water is also produced. That usually we don't recognize because it's just the same. It's hard to see because it's still in water, in solution. And then the other compound is something called sodium acetate. This is a fun compound which you could do some tricks with. So this is a filled out chemical reaction. Now there's a few more things we can put in a chemical equation. Some symbols that we could put above the arrow. Remember, the arrow separates the reactants from the products. So here we have reactants on the left side, and here we have products. Now sometimes to get the reactants to go and react, you need to help them out. So you would need some heat. So oftentimes heat will be written above a chemical arrow, or this triangle also means heat. This means the same thing. You can also cool a reaction down. Sometimes you have to reduce the temperature for a reaction to run properly, and you can put cool, or you can put the actual temperature at which the reaction should be run. So this gives you more information for how to run the reaction. So up here you can actually put the conditions for which in which the reaction should be run. Another thing you can put above is something called a catalyst. Now a catalyst is another chemical that actually is used to speed up a reaction. And the catalyst itself is not used up in the equation. So if you have reactants and then you have products, you may need another chemical, some sort of chemical that is placed above here. I just put a catalyst, but the chemical could be O2, it could be titanium or something. Some sort of chemical that goes above, and the reaction won't run without this chemical present. But it does not go into the products because the chemical does not get used up. You can actually keep using it again and again and again. It's kind of a strange idea, but it's true. This here is called a catalytic converter. Catalytic converter. It actually sits on cars to help purify the exhaust, to help react the exhaust properly. And all cars have to have this to pass emission to be allowed to drive. And in here you have a catalyst inside of here. Actually, it's a metal catalyst, an expensive metal catalyst that helps the reaction along to speed it up and make sure it completely reacts. Oh, and actually above the arrow there's an MnO2. In this case, the catalyst is MnO2. And then finally, let's show you how we write exothermic or endothermic reactions. You've heard this before, but exothermic means releasing heat, endothermic means absorbing heat. And reactions obviously have a heat component. This is a way to recognize you have a chemical change is there's a heat change, there's an energy change. So obviously a reaction that's a combustion reaction which produces a bunch of heat, that heat is a big part of the reaction itself, so we could probably put it in the equation, and we'll show you how this is done. You can also have a reaction that absorbs heat. It doesn't produce cold. Cold is just the absence of heat, but it absorbs heat, and this would be an endothermic reaction. So these are practically a lot of chemical reactions. The only reason we run them is for them to get us heat or to absorb heat, to give us cold. So we have to recognize this and be able to show this in an equation. And here's how we do it. We can write heat as a reactant or a product. So for example, in this case, we write heat as a product, which means this is exothermic. If we were to write heat as a reactant, if for example you needed to heat the reaction for it to go, then it'd be an endothermic reaction. So if heat was added here, then that would be an endothermic reaction. And then a fancier way of doing this is the way we'll do it in an honors chemistry or even a regular chemistry course, is to use this symbol here, delta H. Now delta H is the change, in this case the delta means the change in heat. And the change in heat can either be positive or negative. If it is negative, then this means exothermic. And if it is positive, this means endothermic. So for example, for this reaction, we would say delta H equals negative, and you can actually put the number down, 425 kilojoules. So we can actually tell exactly how much heat is released for the equation itself. Now, we're not going to do much with the delta H in this class. However, you should be aware of the fact that heat is a very important component of a chemical equation. So this ends video 4 for us, shorter video, and video 5 will continue on.